And let's get started. So, welcome back. Happy Monday and happy November. This is our last month of the semester. We are really close to being done. There is a lot of work left remaining. In terms of topics, there's a lot of things I want to cover as well, but it's really not the end of the world. I mean, we'll get to that last set of topics, and we'll get to a reasonable stopping point, and then that'll be at the end of the semester, and that's okay. We've done pretty well given the some of the limitations of this semester, both the format and the compressed schedule we had this semester. So I'm pretty happy with where we are. You may have seen an announcement from me this morning. I had it planned for a while, but I hadn't typed it up yet with regards to this final project that's coming up in these last few weeks of the semester. I'd like you to give it a good faith try, is basically what I'm asking of you. So it's really a project that should be a 4 week project, and we don't have 4 weeks remaining. So there's a lot you can get done in the time remaining, and I've scaled the points back accordingly so that you can get a full score. You can get 100% on this assignment, even though you haven't really completed it. So that announcement kind of lays out how you can get to your 150 points on Project Part C, and I do believe you'll be able to do it based on what I've been seeing in Project Part B, where a lot of teams have been able to really successfully complete it. Um, that's just the last few weeks. So that's maybe it's a little disappointing that you don't get everything working that you want to get working. You can certainly try. You're very free. Feel free to try and get more points for that assignment. It's all fair game to continue to make additional progress. But in terms of what I'm now expecting out of everyone, it's something of a scaled back requirements. We won't get all of the mechanisms that we're talking about in finishing up today in class working in the lab. It would be nice to. There's just a lot of edge cases. It takes a whole week of just testing those edge cases, and we just don't have that week this semester. So do your best. Try to have a little bit of fun with it, and let's all just finish up the semester strong here. Where we left off on Friday is we were still talking about the forwarding. If we want to, remember back all the way back to last week, right? We did a lot of work in understanding data dependencies, and we're just trying to walk through what that logic would require to detect those dependencies, specifically the dependencies that we can actually do something about at runtime, that we can allow our execution to continue even though the register file values, the values in the register file are old, are out of date. So detecting which of those conditions can still be resolved via forwarding and what those logic equations look like for it. We haven't really laid out what the hardware looks like for it, but we have laid out the equations. And at this level, I would expect you to be able to just do a very quick behavioral implementation of it. So our general strategy is this in terms of looking at the multiplexer inputs to our components that consume values. So for the MIPS processor, that's the ALU, and that's potentially the memory stage for the stored data and the store word instruction, and then determine which producing instructions that came beforehand potentially have the value that this instruction is going to need. Did it generate that value? It just hasn't written it back yet. And we're doing it just a comparison. So it's those 5-bit values in which we're encoding the register addresses, the destination address for the producing instructions and the source addresses for the consuming instruction, and just checking if they're the same. And not just checking if they're checking if they're the same, which could be a coincidence, and also the control signals correspond to the fact that there's a writing of a value and then followed up by a reading of the value. So your logic's going to wind up looking something like this, right? We have those muxes that we're adding to our data path. Um, and the book says to make existing muxes larger. I would just add separate muxes just for specifically the forwarding cases and checking to see which of those conditions are true and setting the output accordingly. So the values here are kind of arbitrary in terms of, the encoding of forward A versus forward B. You probably want to have some good comments or some good documentation keeping track of what a forwarding signal means for your design. It's going to look a little different for everybody, right? This is the sort of textbook naming conventions for those signals. Based on the designs I've seen, you're all calling them slightly different things, and you have to keep track of what that means as those signals are propagating in your pipeline. In general, you want to keep your signals named the same from one stage to the other, just with some sort of either prefix or suffix saying, this is my register write value address, my register write address in the EX mem stage. However you want to call that, you do want to label it accordingly. because you'll have that signal in multiple stages at the same time, and they have to be named something different, right? They're different physical wires because they're separated by those pipeline registers. You can create structured data in VHDL that's perfectly synthesizable, or this could just be a prefix where there's like an underscore here versus the dot operator here. Um, you have to keep track of those signals. And then in terms of your implementation for the forwarding logic, it's actually going to look a lot just literally like this. So yes, early in the semester, we're building an ALU. We're trying to understand the low level structure of an ALU. So we're doing it on a bit by bit level. And now we're doing a 5-bit ALU of a type. And I'm just saying, just use the equal operator. And you can. And that'll synthesize just fine. Arguably, it'll synthesize more efficiently than if you tried to use an ALU to build a 5-bit comparator operator. And certainly from a source code readability perspective, from a maintainability, updatability perspective, that's the way you're going to want to implement it, either in data flow or in behavioral logic for these forwarding conditions. But otherwise, that's all it's going to be. It's a scenario that we can detect when we look at the code. We know when there's those read after write dependencies. There's a specific subset of them that we can actually do something good about. We can forward the values on, and those are muxes. And so for those muxes, they're being driven by these and other similar conditions. So that's where we left off on last Friday. We also talked about this as kind of an interesting scenario or version of this we talked about on Friday is an interesting scenario in which you could have kind of like the double forwarding condition where this would be a forwarding condition, but this instruction has that dependency on the previous one and the one before it. And we know logically, okay, we want the most recent value, right? We want the most up to date value. Logically, we look at that code and we know it's the output of this instruction that we want to correspond to the value that's being read by this next instruction. But we have to tell our forwarding logic to be aware of that. And it's ultimately just more conditions, right? So we only want to forward from the slightly older instruction if we don't want to forward from the more recent instruction. You could do some sort of priority encoding scheme. You could have multiple levels of muxes would be another way to potentially do it, where the more recent forward happens after the least recent forward. The textbook approach to this is to directly encode that priority in the logic equations themselves. And that's what we're seeing here. It's getting a little bit wordy looking here, these equations. It's why we want to do it in our high level, behavioral or data flow VHDL so that we don't have to keep adding new ALUs and structurally wire all this up together. But we could walk through what it's saying for that memory hazard. For that instruction that's 2 instructions away from our current one, we only want to do that forwarding if our condition is true, which is here. If this basic condition is true and the other forwarding condition is not true. And I think I'm guessing some of you are already looking at that textbook representation of that and realizing, well, I can be a lot more clever than that in how I implement that. I can separately have a 1-bit signal corresponding to those, and then I can just check that 1-bit signal, and that would be a perfectly valid implementation. Um, the synthesis tools should be smart enough to catch that as well. So in terms of the hardware that's generated, it's not necessarily any smaller because it should be able to detect that this term, this blue highlighted term, is used here, and it's also used in the in this. Let me make sure I'm in the right place. It's also used here in this expression to determine whether we're forwarding from the EX age. It's the same exact logic. It should be able to replicate that. Instead of replicating that logic, it should be able to fan out that logic and do the same exact logic for those 2 different purposes there. So don't get too clever with it as you're implementing this for Project Part C. Go with very basic, vanilla, straightforward VHDL. Let ModelSim and let the synthesis tools do the work for you in terms of figuring out what the most efficient circuit is for something like this, and just focus on the correct functionality. That does reflect, as I mentioned, kind of a shift in perspective. Um, at some point, we're no longer caring about learning digital logic design, and I think we've reached that point once Project B is done. And now we're focusing on understanding computer architecture, and we do want to use higher levels of abstraction when we're wanting to build something that has more complex functionality. And I mentioned that to a couple people who have been asking about next semester. Are you going to take 480? Are you going to take 488? Both of them, 488 has a 2-week VHDL module in it. 480 is a good chunk of the semester is doing VHDL again. The code's not going to look at all like your 381 VHDL. 381, we really care about understanding the low level digital logic as a supplementary learning outcome in addition to the architecture. So that's why we build the ALU by hand, bit by bit. Same with our register file and so forth. We build it structurally. Structured VHDL is still very good for understanding structure, but when we have a lot of functionality we want to implement, and as you gain that familiarity level with behavioral modeling in VHDL, your code is going to wind up looking quite a bit different. And it's very possible, if not by the end of this semester, because we got a lot going on this semester, by the end of next semester, as you take that follow-on course, I think you'll be able to look back on your 381 projects. Project Part B is probably the best example to look at and realize, oh yeah, I could probably have done that whole thing in 50 lines of code. Um, it's which 50 lines of code is the tricky part, but it can be done in a very efficient way, using behavioral modeling. So this is kind of our in-between stage where yes, I could make you do all this structurally, but it'd be very painful. And you'd be tweaking it and changing conditions and doing all that structurally is quite painful, as some of you have discovered this semester. So we just do it behaviorally, and we trust the tools to take care of it for us. So you'll get that experience next semester if you're not going to get that experience as much this semester, depending on which of those follow-on classes you wind up taking. Okay, I'll get off my soapbox there. But so again, as we saw last week, this is what that pipeline winds up looking like now. Again, it's got a lot in common with your single cycle Project B processor, right? The fundamental difference is we've split it up to these with these pipeline registers that are keeping track of all the state, all the intermediate signals that in your B processors were just a wire, which is a single signal. But now we recognize that for many of those signals, we have to hold on to the value for multiple cycles. The value to be written back in your Project B processor, if it's an ALU instruction, could directly be connected back, right? You'd have a MUX for memory or ALU output, reg or mem, whatever that control signal would be called, and it would be directly connected back. You would just be adding that MUX. Now, because we aren't writing back until that one cycle, two cycle, that third cycle afterwards, two full cycles afterwards, after we've calculated the value, we have to store that intermediate result. Same for the values we've read from the register file, right? We can't use them right away. We can't directly connect them to the ALU because when we're in this cycle, a previous instruction is currently in this cycle or in this stage of the pipeline. And so we can't connect it directly. We have to hold on to it for a cycle. That's all that those pipeline registers are doing. They're holding that intermediate result for us so that we can use it in subsequent cycles for that given instruction. And this is also why our control scheme kind of has that sort of staggered view to it. There is no harm in not overthinking how you pipeline your control signals. The textbook approach, which is also appropriate, is showing that as you generate your control signals in cycle 2, there's control signals that are going to correspond to the execution stage, like ALU source, some control signals that are going to correspond to the memory stage, like memwrite, and some controls that are only going to correspond to the write back stage, like regwrite or mem or reg signals. And we can actually drop off those signals on a stage-to-stage basis. The arrow's not being shown here, but this little block, which is abstracted away as just being EX control for that instruction, is going to have those wires peeled off and connected to the ALU. That's our ALU op. That's our ALU source. And then we don't actually need them anymore. But the other ones we still need, so we actually pipeline them again, additional cycle. And then the memory signals go here. They connect to our data memory, our memwrite, our memread, whichever ones we're using at that stage. And then we don't need them anymore. And then finally, our write back signals we still need up until the very end. So that gets pipelined all the way through our processor because we need them 3 cycles later after we have generated those signals. But if you decide that the signals are all the same, just pipeline them all the way through and keep the EX signals a cycle longer than you need them and keep the memory signals a cycle longer than you need them. It's not going to break your processor. It's still going to work just fine. You'll just have extra signals that you're not really using in that stage. It's up to you. Whatever you think is easier for keeping track of the signals that you have in your design. It is going to be a little bit tricky, right? And that's a good chunk of the points for Project Part C. These are just registers, which we know how to do. We have our n-bit flip-flop. That is ultimately what they are. But keeping track of what needs to be in those n-bit flip-flop, how big n needs to be for each pipeline stage, is a big chunk of the challenge of Project Part C, as we talk about in a moment here, how we deal with the edge cases associated with those pipeline registers. Because otherwise, the functional units aren't changing at all. Yeah, you have to build a new one. This is new. This didn't exist for Project Part B at all. But I'm already telling you, VHDL wise, it should just be a few lines of behavioral code. Don't make it super complicated. Just have a separate unit that's implementing those equations that you've agreed upon with your project team. The real challenge is then in implementing these pipeline registers in terms of understanding what they need to do and what needs to go into them. And then ultimately the challenge is a debugging challenge. It's 5x the debugging, arguably, right? I mean, that's one way to look at it because you have five things going on at any given time, five instructions going on at any given time. Instead of just looking at that vertical slice of model sim and knowing everything you need to know about that instruction, now you're looking at like a staggered five slice for a given instruction and having to follow it through each stage versus just following it all in isolation for a single cycle there. So we had mentioned this, but let's get back to it with regards to our read after write dependencies and our read before write data hazards. There's the two that we have to be able to detect. We'll show them here again. There's a two that we have to be able to detect because we can forward them. We can fix this because the write back doesn't happen until cycle 5, and because we only need the value in that at the end of cycle 5, but because we need the value here and it gets produced in the EX stage, we can actually do that forwarding, right? So we can detect when this is happening because we can resolve it. Our processor can work as if nothing was the matter, as if this dependency didn't even exist, basically, when it's this type of data dependency. But we had talked about it last week that there's a special case of this when there's a load word as the producing instruction. And the reason, again, it's a special case is nothing unique about like load or its encoding or anything like that. It's just because the value that we want to forward isn't known yet. For our ALU instructions, this is the value we want to forward. We know it at the end of stage 3, cycle 3. For load word, we only know it at the end of stage 4. So if there's a load instruction immediately followed by a use instruction, an instruction that takes that value and does something with it, we can't forward. The values just aren't ready in time. We showed that visually as we graphically laid out the pipeline. Right, the arrow was still going backwards in time when we were doing that. But that's the same concept. It hasn't changed from last week to this week. It's a specific case only because we can't fix it via forwarding. We have to go back. We still have to go backwards in time. Our code is still using a stale value, even if we put forwarding in place. It doesn't work right. So that is a special case for this MIPS pipeline where it's a data dependency, it's a data hazard, and it's a special data hazard. They're all data hazards, but it's a special data hazard because we can't fix it via that mechanism. Detecting it still is going to look very similar, right? It's the same concept. We have this instruction that has a registered destination. It's the RT field, right, of our itype instructions. Has this registered destination address that is equal to my instruction's register source address, one of my source addresses. So that logic is exactly the same. And that producing instruction is a load word, which you may or may not have had a control signal uniquely for load word. That mem to reg is probably the signal you could use. If you don't want to, remember that, always create an instruction called is load word, right? Even if it's superfluous and it's only used for this purpose and it's exactly the same as mem to reg, or in the textbook it says to use mem read, but we're not really using mem read. You have that signal that tells us not only is all of this other logic true, yes, it's a data hazard, it's our special data hazard because it's not going to work out. And we can detect that early. We could wait until it's too late if we wanted to, but we can detect that as soon as those two instructions are in the pipeline and have been decoded. So that's why this is showing values that are being compared between something in the IDEX register and the IFID register. Technically, the same logic would also apply if we did it one cycle later, but we have to tell the processor we have to stall, we have to wait. Let the load word instruction continue, but that previous instruction has to wait. You could do it one cycle later, but then you have to tell the two next instructions to wait. In this case, you only have to tell one instruction to wait. But that's our load use hazard. So that's our so-called stall condition, right? We already know that we could do this via software. A compiler could detect this for us and insert a no-op. What we are basically doing is dynamically inserting a no-op into our pipeline. Load followed by use has to become effectively load followed by no op followed by use instruction. And that's what it means to stall our pipeline. We're telling that use instruction not to continue for one cycle or until the condition is not valid, but that'll just take one cycle for us. And whatever was in that pipeline stages, we have to replace with zeros. Or zeros probably will work just based on how the MIPS processor is designed, the ISA is designed. You have to insert something that doesn't mess up your processor instead. Zeros will probably work because your reg write is probably 0 for don't write, and same with mem write, but it's based on your control scheme, what values you need to insert to make sure that nothing happens in that little bubble cycle there. No op should work. That's, shift left logical 0 0 0. But however you encoded your control scheme, you'd be inserting a, a non-state changing instruction when you're stalling your pipeline. And I mentioned this is part of the challenge and or pain of Project Part C, and you will be still expected to implement this. Um, what does it mean to actually stall your pipeline? It's all about the input and output of those registers. We think of this pipeline progressing in this orderly fashion, but as we see here, there'll be some cases where it's not orderly. So that has to do with both the write enables on those pipeline, meaning don't update some of those write enables on your registers, as well as taking the value that's currently wanting to progress down the pipeline and making sure instead we've inserted a bubble, inserted that no op or inserted that anodyne instruction that doesn't really change our operation of the processor there. So that does require just forcing some of those values to 0. Um, it really depends on how you implement it, and there's not one exact way to do it. You can have a reset line potentially use that first for forcing the values to 0 for those control values. You can replace it with a mux that just muxes in zeros. That would also work. So that's separate, kind of separate from the pipeline, but you could combine all that together in one module and call that a pipeline register. And then you need to make sure that that instruction that's both in the program counter or that program counter and the instruction that's in the IFID register don't get updated. They stall. It's really just one instruction, but it's the program counter that's also not updating because then we'll wind up skipping an instruction if we're not careful. So that does have to do with the write enable on those signals, on those registers that we have there. So graphically, as we lay it out, it makes, I think, some sense that we have our load followed by our immediate use instruction. And as soon as we can detect that, we're inserting a stall. Whatever was in this register in which we know there's a possible issue, we want to make sure zeros get propagated down the pipeline instead. And likewise, we want to make sure that this instruction doesn't continue for at least one cycle. And that requires stalling the program counter as well, but stalling this register. Don't update this register. Even if there's something new that we'd really like to update the register with, hang on to it. And we've fetched whatever that next instruction is going to be, but just hang on to it. Let everything wait for a cycle. So really another way to visualize what's happening there is it's really that instruction memory stage where we're telling it, don't continue. Stay there. The current instruction that's somewhat dangerous, insert zeros instead. Again, whatever that means for your implementation, insert zeros instead for that instruction. And whatever's in the program counter, you can think of it as the memory also being stalled, but for us, it's really just the program counter being stalled. Hang on to it. Hang on to that program counter for just one cycle, or arguably the correct way to think about it, hold on to it until that hazard condition is no longer true, which will just be one cycle for our implementation. In a deeper, more complicated pipeline, it's as long as you need to hold on to it until it's ready to proceed. But for us, that's just for one cycle there. And again, the reason that works is because we can detect when it happens, and we can detect when it happens pretty quickly. And by inserting that bubble, inserting that no op, we still have the hazard. It still exists, right? But now it's something that we can resolve via forwarding. We've let that load word get an extra cycle ahead of our use instruction, so we can detect it and now detect that there's an extra cycle between them. The value will now be available in time for us to use it. So that arrow is now no longer backwards in time anymore. For this pipeline, stalling for one cycle is going to be a valid solution for almost everything we want to do. As it gets more complicated, you really have to kind of have a bookkeeping of each instruction. How far along is each instruction in this potentially variable length, potentially very long pipeline with many, many instructions active at one given time? And there's almost like a software kind of schedule that allows certain instructions to proceed when it's time for them to proceed. For us, though, there's just these couple of edge cases, basically. In this case, our load use edge case, we wait for one cycle. It's still a load use, but it's got that extra bubble between them, so we can forward now. So our data path doesn't look that much different. Just like we had this forwarding unit that's sort of sitting in between our pipeline stages, it's not entirely part of one stage, it's kind of crossing two stages here. We have our hazard detection unit that's looking at information across two pipeline stages here. Our input is going to be the very similar looking control signals, the RD or the RT field in this case of the mem instruction, the load word instruction, and then the RS or RT of our current use instruction. If that's true, and if it was a load instruction, which is what this signal is encoding for us, at least in the textbook version, something's wrong. We have to check for it. And that control logic is going to be connected to both the program counter as well as to this pipeline register. I think in terms of how we implement this in the lab, this could directly be connected to just the write enable. For us, in terms of how we implement our stalling of this instruction, we have to connect it potentially to the write enable as well. And we also have to make sure that what's currently in this stage gets replaced with something safe. Could just be a big mux on the instruction field and just replace it with all zeros. I think that will work for everyone's implementation. But in any case, it's a little bit implementation specific. Both pause the current instruction and let whatever is progressing in its place be something that's not going to mess up your pipeline state or your processor state. Just a no op. What and all zeros does is the pseudocode for a no op or what it assembles down to. So replacing the entire instruction with zeros should work for your purposes. This is a little bit of a subtle point because we just talked about how we resolve this load hazard via detection and a stalling of the pipeline. Um, Nowadays, the compiler has a very big responsibility to do this as well. Um, so ideally, we as the compiler can look at our assembly code and generate code that's going to be less likely to stall. For the same reason that right, a data dependency like a read after write is a very natural thing to generate as a from a programming language's perspective. We write a variable and then we want to use that variable, read that variable. We know that the only issue, at least for these data hazards, that causes a real problem in terms of performance is a load word immediately followed by a use of that load word value. And again, that's a natural thing. Read after write is something that's going to always be happening in our code for anything that's doing real work. But there's usually enough flexibility for the compiler or for us as the compiler to recognize, well, just don't do exactly that. Right? Usually we have more than one variable we care about at a time. Usually there's more than one thing we need to get done in our program. So oftentimes there's some ability for us to reorder our instructions such that the code is still doing ultimately the same thing. And maybe it's slightly less logical the ordering in which you've encoded it for this reason, but it's still going to be correct via that reordering. And we've just inserted a valid instruction after our load word instruction. A valid instruction that doesn't use the value loaded by that load word instruction. So again, this is a little bit of a subtle point, but the point is, if our compiler or us as the compiler is able to fill that load use slot or that load delay slot after our load word instructions with something valid, with something that's doing work that our program requires, but just so happens to be instruction that doesn't cause the load use data hazard to cause us to stall for one cycle, well, then that's a win-win scenario, right? That next instruction that we reordered had to get done anyway. We had to do that instruction anyway. We've just moved it up to where this previous instruction was, and now we don't have that extra cycle of stall. Compilers can do that. And if a compiler can't do that, maybe it'll just say, let's just insert a no-op. That's what we're referring to as the software scheduled pipeline for project part C. It is let your code run and insert no-ops where otherwise, if there weren't no-ops, your code would be wrong if you don't have this hazard detection and forwarding logic in place. But even with all that logic in place, we may still want to do that as the compiler. Because, yes, we can detect when it happens, we can stall the processor for a cycle when it happens, but wouldn't it be great if we didn't have to do that? Why waste a cycle if we don't have to, if there was some valid work for that pipeline to do? That's also referred to very historically as an interlock, where two stages are kind of interlocking each other because of that data dependency. And that was one of the marketing points of the original MIPS processor publications and even resulting products from it, which was it was a microprocessor without interlocked pipeline stages, and that's it was a bit of a backronym, but that was one way they referred to as MIPS, as it's a processor that has pipelines that don't have interlocks because there's just a couple scenarios and the compiler would take care of those for us. The reason this is kind of a little bit of confusing is because what we just designed or what we just talked about is a hardware interlock. So it has an interlock. It doesn't have very many. I guess that's still a nice thing about it. But modern pipeline processors are going to generally need to have some ways of stalling instructions for this purpose. But it's the role of the compiler to try to minimize the amount of times that has to happen by reordering instructions for scenarios in which it's aware of the pipeline's implementation. By reordering these instructions, you'll get slightly better performance. That's very compiler dependent. That's very pipeline dependent. It depends on what we tell the compiler about our architecture, what it knows about our architecture, the extent to which it can do that reordering. I think we made that way more complicated than it needs to be. I think this part is all that matters. Ignoring the acronym and whether it's true or not anymore, it doesn't matter. But we can detect the load use delay and our code is still correct, even if we have to stall for that cycle. But as a compiler, or as us, as those we are the ones reordering our assembly instructions, we can do so to avoid that happening. But we can't always avoid it. So we either have to have a solution in which we're always inserting a no-op, or we have to build our hardware interlocks, have to build our hazard detection unit that stalls the pipeline. So for project part C, we're kind of doing it both ways. We're starting off with a pipeline processor in which we have no forwarding and no hazard detection logic because we want to get that part working first. That's what we refer to as the software scheduled pipeline, where you as the compiler are responsible for inserting hopefully the minimum number of no-ops to get your code to still work correctly. But the original MIPS implementation was able to do it without any hazard detection because as the compiler that came along with it was attempting to fill that slot with good stuff, with an instruction that's still valid but didn't have that data dependency. And if it couldn't, it would generate a no-op instead. That was more complicated than it needed to be. It's Monday. What can I say? All right, moving on. Okay, moving on. That was data hazards, and you'll get pretty comfortable with them because you'll be implementing them. You'll be analyzing the data dependencies, and you'll be trying to understand basically that logic and how to implement that same logic. There's enough complexity in Project Part C before you even get to that point. Just getting the pipeline registers working and testing data as it flows through the pipeline. But that's that next phase of that Project Part C processor that you're implementing. Those are data hazards. The second hazard, and we've already kind of talked about this a very little bit, it refers to control instructions and control hazards. Because of this pipeline, we are making a fundamental assumption about how our instructions are being fetched and loaded and executed through the pipeline, which is from one instruction to the next instruction to the instruction after that. And for instructions that are PC plus PC equals PC plus 4, that works just fine. But we already were kind of starting to see, even when we introduced the basic concepts of a pipeline, that, well, for those control instructions, for jumps and for branches, essentially, that's going to cause extra problems. When the PC is not going to be equal to PC plus 4, this is a different scenario than in our single cycle processor. In our single cycle processor, we just had to add that logic in that single cycle to detect when that happened, based on opcode, based on ALU output, based on a couple of AND gates to figure out which type of branch it was, or if it was a jump, an extra mux. We set the next PC. But in our pipeline processor, in cycle 1 or in stage 1 of our implementation, we have no idea what's happening to the instruction yet. We don't know what kind of instruction it is yet. We haven't decoded it yet. And even in cycle 2, at least in our current implementation, where we've decoded the instruction, we haven't executed it yet. So we may know that it's a branch instruction, which is helpful, but we don't know yet if it's been taken or not, or needs to be taken or not. So we have 1, potentially 2, if we're not careful, potentially 3 cycles in which the PC plus 4 values are being updated and instructions are being fetched, and those could be wrong. We weren't supposed to actually fetch and execute the PC plus 4 and then followed by PC plus 8 instructions here. That's what we refer to when we talk to a control hazard. You can think of it as a data hazard on the program counter, because that's what it basically is, right? It's a data dependency on the program counter from one instruction to the next, because it's kind of hidden, right? In the back of every instruction is we also update the program counter, right? That's a separate side effect of every instruction. That's one way to think about it. And so for our control hazards, for certain instructions, we have a read after write error with our program counter. And so we have to treat it as a special case. The nice part about control hazards is branches are not as common as data processing instructions. Every 10th instruction is a branch, roughly, right? Depending on benchmark, but that's a rough order of magnitude estimate. Roughly every 10th instruction is going to be a branch instruction. So it doesn't happen that often. It's a problem 10% of the time. The downside, that's the positive view. The downside is, unlike for our data hazards where there's just that one edge case we have to detect, and the compiler can often insert something valid anyway, so we don't even have to worry too much about that one edge case. There's nothing that really fixes control hazards. It's a fundamental shortcoming of pipeline processors. So our fix is basically, how do we detect when it happens? How do we correct when it happens? We're not going to very easily be able to get our ideal performance out of our control instructions. So jumps, just to start with, are going to incur 1 stall. We don't know it's a jump instruction until that second cycle, because we haven't decoded yet. That's where our decode logic is. And the argument is we can't decode any earlier. We spend the whole first cycle fetching the instruction, so we can't really decode it as well, right? So we spend that whole first cycle decoding the instruction, in fetching the instruction. We spend that second cycle decoding the instruction. That's as early as we can know that it's a jump instruction. The nice thing, at least about a jump, is it's a jump. We know it's taken. We know we are jumping. So our fix is also relatively straightforward. Is we know what we need to know. It was a jump instruction. Whatever we actually updated with our PC plus 4 and put into our pipeline register here, we just got to squash it or flush it or obliterate it, whatever word you want to use. We have to replace it with something that's not valid, or which is a no-op, which doesn't break our processor pipeline. Whatever that PC plus 4 instruction got fetched, but it didn't get too far along. Okay, we lose a cycle here. So this slide says jumps are relatively straightforward. I'll agree with that. What complicates that in terms of our implementation, which is different than the textbook implementation? Question for you as a class. For those of you who are still with me today, I've lost the plot myself, but for those of you who are still with me today, textbook says, well, jumps aren't too big of a deal. 1 cycle, or put something valid if you can, but 1 cycle happens 3% of the time. And we'll talk about that in terms of our other possible solutions. There are other possible solutions, but this is our starter solution. Yes, Take the penalty every time you jump and just live with it. Our jumps are a little bit more complicated than that. Why is that? And it's not our jumps. More realistic instructions that we have to support in our myth processor are more complicated than that. Why so? Okay, there we go. Josh, thank you, sir. We have more complicated jump instructions. Jump and link is probably going to be okay, but it's both a control instruction and a data processing instruction, right? We're both jumping, and we do got to make sure we're actually writing back to the register file. So that instruction still has to do more work. We have to definitely implement that. Jump register is a problem for us, right? Jump register um, is a use instruction. So if we're not careful, we could have, and this is going to be a very common thing, right? I mean, you have function calls, and sometimes those functions are short. So it's very common. It's not a weird edge case to say we have a jump and link instruction very quickly followed by a jump register instruction. Maybe it's a one-line function. They exist, right? I mean, maybe it's it's a leaf function that's doing very little work. That jump and link followed by a jump register is both an example of, well, two control hazards as well as now a data hazard, and it's one that the textbook doesn't talk about at all, right? So jump and link is producing a value, specifically the RA register. It's hidden in there, but it's there. It writes to register 31 the PC plus 4 return value. And by the way, we had some discussion about this, whether it's PC plus 4 or PC plus 8. Well, this is all interrelated facts, right? The reason it could be one or the other depends on how we implement our jump logic for dealing with our pipeline. But in any case, it definitely produces some value that gets stored into our RA register, and then that jump register is also now using that register. So it's both a scenario in which we have a potential flushing for the PC plus 4 value, as well as it's also a data hazard that we have to check for. So that's something that if we want to get Project Part C, all 5 weeks of it in our 3 weeks of time implemented, we'd have to support that case as well, because that's not a synthetic edge case. That would be an actual operating case that we would see quite commonly in code that have smaller functions. Yes, but to start with, our solution for jumps is to stall. We'll talk more about this at this point. Who knows when, but we'll get to it. So that's you can think of it as a data dependency in time with regards to the value that's in our program counter. With branch, it's a little bit worse than jump because our implementation in jump tells us, well, we have everything we need to know potentially with the jump register, but we have everything we need to know right here. So yes, we lose one cycle, life moves on. It's not ideal. That's our current implementation based on the textbook representation. For branch instructions, though, our project part B implementation tells us, well, we have to fetch the branch. We have to determine whether it's a branch and fetch the register values. And we actually have to calculate the branch logic, right? Does the branch get taken or not? If it's an equal or a not equal, we have to check what the zero flag is out of the ALU. That's 1, 2, 3 cycles later. So at least in the naive implementation of our branch instructions, we have to potentially flush for 3 cycles. And that's pretty painful. I said branches are, roughly every 10th instruction. We have to stall an extra 3 cycles every 10th instruction. We've really hurt our CPI, right? Our CPI is nowhere close to 1.0, which is our ideal for this scalar pipeline that we have here. What other approach could we do to somewhat minimize this pain? Any thoughts? So again, the cause of this problem is based on how you've implemented project part C or part B so far. We don't know the results of the branch until the end of the execution stage, full 3 cycles after we fetched it. That's a possible solution, Tyler. You could argue that is our current solution, right? By taking PC equals PC plus 4, we have assumed the branch is not taken. And so you're right. We only have to do this flushing when the branch actually was taken. So that is a nice kind of side feature. It's not just the number of total branches that cause those 3 cycles of stall. It's the number of branches that are taken that cause those 3 cycles of stall. And that's a good point. And our logic has to be aware of that. If it's not taken, no harm, no foul. Those instructions that we fetched for PC plus 4 were the right instructions that we wanted to fetch in the first place. So be it. What else could we potentially do? That is a valid answer. Absolutely. Thank you. It's the next slide. I guess anyone who like clicked ahead gets the answer there as well. But thank you for looking one slide ahead. If that didn't come straight from you, um, we have all sorts of now these sort of one-off comparator units that we're already inserting into our pipeline. Trying to minimize the amount of comparator logic is clearly no longer a design criteria for us here, right? And we also have multiple ALUs in our data path as well for PC plus 4 for this main ALU. All those comparators are basically mini ALUs as well. So while for the project part B implementation, there was no reason not to just use our primary ALU to determine equal or not equal, because of this exact issue of that's just too late. That's happening too many cycles late for our design from a performance perspective. That is our potential solution, is to put in enough extra hardware so that we can test those registers as well as calculate the branch address and updating the PC as early as possible, which would be the second stage of the pipeline. So to put that as early as possible, um, I can already hear some discussions. Well, doesn't that affect our critical path? Because now there's that much more stuff happening in here. Yeah, that's a trade-off that we'd have to truly understand. We can't say for certain that that was our critical path. But if we do assume the stages were roughly balanced by design, then that may hurt our clock frequency. But pushing that aside for now, this solves the problem of having to stall for additional cycles by basically replicating what was all of our branch logic, which we had over here, and putting it back here. As soon as we read the registers and have decoded the instruction, do our comparison, do our branch equal slash branch not equal. And in doing so, we still have this issue where a branch taken means we fetched an instruction we weren't supposed to, but it's just one instruction we weren't supposed to. So that's not so bad. So it's closer to the jump scenario in terms of our control hazards and our branch for jumps, and our control hazards for branches have the same penalty associated with them. One cycle of stall associated with every single branch slash jump. Still not great. Still not as good as what we can do for our load use scenarios, but not as bad as it was if we had to wait for 3 whole cycles. And our pipeline kind of looks like this correspondingly. It's starting to get a little complicated, but this is pretty close to the final pipeline that you would be implementing for project part C here. All the changes associated with this are in that second stage now. We have all the information now with that change that we would need to be able to detect whether or not there's a control hazard in stage 2. It's a little subtle what all is going on here. I'll try to explain it as best as I can. Um, there needs to be logic to determine. It's not actually not all being properly shown here, but there needs to be logic to determine, our immediate and our sign extended shift left to branch logic for calculating what the branch target PC would be. We need to actually read the registers, and then we actually need to also add a little comparator here. It wouldn't exactly be, well, it'd be an equal slash not equal unit for your implementation to support both branch equal and branch not equal. It's a comparator unit that we would take the output of and determine whether our branch should be taken or not. That signal's not being shown as being connected here, but it would need to be connected back to this unit as well. And our logic then for that hazard detection unit would essentially be if opcode equals a jump type, one of those 3 opcodes, or if opcode equals one of our branch type and branch taken, then flush install. Or flush that instruction. Don't actually execute that next instruction. Otherwise, continue on. Move on to that next stage. That definitely impacts our performance still. Just based on our CPI equation and our understanding of performance as it relates to CPI, if our ideal is 1, and if 15% of our instructions were branches, our CPI is 15% worse, right? That definitely impacts our performance. So that is why I mentioned that there's no solution as nice for control hazards as there is for data hazards. We'll talk a little bit more, and this will be on Wednesday at this point. We'll talk a little bit more about different solutions for our control hazards. But architecturally, even given now decades of research and different approaches to dealing with control hazards, there really is no solution that quote unquote solves the problem. It's not really a solvable problem. It's program decidability issue, right? There's theoretical limits about what we can know about whether or not a branch should be taken. What we'll talk about starting on Wednesday, because we're not ready for caches quite yet, would be an approach that's attempting to predict whether or not a branch is going to be taken or not. Because if we can predict it accurately, and maybe you've heard the term branch predictor before, we can prevent that delay cycle from happening here. In a sense, we have already built with that circuit a basic branch predictor, but it's always assuming branch not taken is what it's doing. But there are many such advanced approaches that take into account that branches can be very painful and maybe more painful for even deeper pipelines and attempt to minimize the impact of those. It doesn't zero out entirely, but attempt to minimize the impact of those. Let's leave things here for today. Wednesday's quiz was supposed to be about cash, so that's not going to happen. So no quiz on Wednesday, but come anyway. I'll miss you if you're not here on Wednesday, and we'll continue and just finish up this control hazard topic. We could spend a whole semester on control hazards and understanding the logic required and all the academic and industry work that's gone into improving control hazards and their performance. We'll cover a couple brief options that are available to us for your processor projects for Part C. You won't be implementing any of those. We'll just be understanding basically what they're trying to do. So let's leave things there for today, and I will see everyone on Wednesday. And good luck with finishing up your single cycle processors.